Hi there and welcome to tutorial 17 on discrete random variables, and this is for the Edexcel S1 A-level module. It is applicable to most other exam boards, and as always, if you're looking for further help with your studies, do check out youtube.com/Mr. Arnold's Maths. Okay, so we're going to talk about discrete random variables to begin with. And a random variable is a quantity that can take any value determined by the outcome of a random event. So a random variable, we usually abbreviate to RV, is a quantity that can take any value determined by the outcome of a random event. And random variables can arise from probability experiments. So just some examples of that, we can call say X be the sum of the scores when rolling two dice, Y could be the product of the scores when rolling two dice, and Z could be the difference of the scores when rolling two dice. And do notice that we use a capital letter for our random variable. So we'll always use a capital letter. Now, what else have we got? We have discrete random variables, and discrete random variables can only take specific values. So if you think way back when we learned about discrete and continuous data could take a range of values. Discrete data could take only specific values. So that's what we're going to deal with in these next few tutorials, discrete random variables. And suppose x is a discrete random variable. It takes values x1, x2, x3. So for example, if you think about the sum of the scores when rolling two dice, some of the some of the results we could have could be a 2, maybe a 3, a 4, etc. Okay, so x is a discrete random variable if x takes values x1, x2, x3, etc. And the probability that the random variable takes a particular value is equal to the probability that that variable comes up. Now this notation can seem a little bit confusing to begin with, but it will become much clearer. A couple of conditions: all the probabilities must be greater than 0, and the sum of the probabilities must add up to 1. So that's what this notation means here. All the probabilities, each individual probability must be greater than 0 or equal to 0, and the sum of all those probabilities has to add up to 1. Right, so let's take a look at an example just to kind of clarify what we've been talking about. So we've got two probability distributions here. We're going to try and identify which ones are discrete random variables, and if not, why it's not a discrete random variable. Now, if we remember, the sum of the probabilities must equal 1. So if I add up all these probabilities, let's say 0.2 plus 0.3 plus 0.4 plus 0.3 plus 0.2, adding them all up, 0.2, 0.5, 0.9, 1.2, 1.4, 1.4, so it's not a discrete random variable. The reason being that the sum of the probabilities is greater than 1. Let's have a look at our second example. So again, add up all these probabilities. 0.2, 0.3 is 0.5, 0.6, 0.7, 8, 9 is 1. So the sum of the probabilities is 1. And also, we'll notice that each individual probability is greater than or equal to 0. So that meets our two conditions. So it is a discrete random variable. Okay, time for you to have a go. Pause the video now and see if you can work out if these are discrete random variables. These are all fractions, by the way. Okay, hopefully you've had a go at that. Here are the solutions. The first one is a discrete random variable because the sum of the probabilities does add up to 1 and each probability is greater than or equal to 0. The second one is not, because not all the probabilities are greater than or equal to 0. If I add these all up, I do get 1, but we can't have negative probability. Alright, let's move on to another example. So if x is the random variable, and that random variable is the sum of the scores on two dice, we're asked to find the probability distribution of x. So in other words, we're going to have to fill out this table here. A good place to start is with a sample space diagram. So it's the sum of the scores on two dice. We've seen this many a time, so that's our sample space diagram. We're going to start by going to our table here and filling in what are all the different outcomes we can have. Well, we can have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So they're all the particular outcomes for this event. Each particular outcome is listed here, and now we're going to write down the probability that the random variable takes that particular outcome. So what is the probability that we get a 2 when I roll 2 dice? Well, there's only one option out of a total of 36. So that's 1 out of 36. What's the probability that the outcome takes a particular value of 3? There's 2 out of 36. Now we could simplify that to 1 over 18, but for the purposes of this, it's far easier to leave everything with the same denominator. Next is 3 out of 36, 4 out of 36, 5 out of 36, 1, 2, 3, 4, 5 out of 36, 1, 2, 3, 4, 5, 6 out of 36, and then we'll start going down again. So 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. So that's our probability distribution for a random variable x, which represents the sum of the scores on the 2 dice. Okay, time for you to have a go now. So pause the video and see if you can answer this question. We got 2 fair coins tossed, and x is the random variable, the number of tails, not teen, seen. The number of tails seen. List the sample space diagram and draw the probability distribution. Okay, hopefully you've managed to go with that. This is the solution. So I started by listing the sample space diagram, and then I decided, well, what are the different outcomes? So it's the number of tails seen. So we can have no tails seen, maybe 1 was seen, or 2 was seen. Probability of getting no tails is 1 out of 4, which is here. 1 tails can happen this way, so 2 out of 4, and 2 tails is this way, so 1 out of 4. Okay, let's move on to another example. So we're given a probability distribution, and we're asked to work out what A is to begin. So first thing we must remember is that the sum of the probabilities must add up to 1. So that's useful. So if I add up all these probabilities, 0.2 plus 0.3 plus 0.1 plus A plus 0.2, adding them all together, that must equal 1. That means that A plus, and let's just add these up, 0.2, 0.5, 0.6, 0.7, 0.8 plus 0.8 must equal 1. That means A must equal 0.2. So now we know what A equals. Let's just fill that in our diagram, 0.2. And the last part is find the probability that our random variable is greater than or equal to 2. So what are all the different ways that can happen? Well, there's that way, that way, that way, and that way. These are all greater than or equal to 2. So I'm just going to add up all these probabilities. 0.1 and 0.3 is 0.4, 0.5, 0.6, 0.7, 0.8. So equals 0.8. So just to remind us, the probability that the random variable is greater than or equal to 2 will equal the probability that the random variable is equal to 2 plus the probability that the random variable is equal to 3 plus the random variable the probability that the random variable is equal to 4 plus the probability that the random variable x is equal to 5. So we just add up all those probabilities. Okay, pause the video now and see if you can find k and the probability that the random variable is less than or equal to 0. Okay, hopefully you've had a go at that. Here is the solution. Solving for k, I add up all the k's, I know they're equal to 1. So then I solve for k and I find that k is equal to 1/7. I really hope that you left it as a fraction because it's much easier to deal with the fractions as exact answers here. Don't convert it into a decimal if it's going to be recurring. Next part, find that the probability that x was less than or equal to 0. Well, that's simply the probability that x equals 0 plus the probability that x equals -1 and the probability that x equals -2. So we just add these probabilities together. 3/7 plus 1/7 plus 1/7 is 5/7. Alright, fantastic. Let's move on now to probability functions. So we can also have probability distributions shown using functions. So this is a random variable x again, and it has a probability function given below. And what we see here is actually just the probability function for the sum of two dice. So let's just remind us of what that distribution looked like. That was the distribution we worked out earlier on. And let's go and see how it matches up with this. So if I think what is the probability that we get a 12 when I roll two dice together, what I do is I substitute 12 into my function. So when k takes any of these values, it goes into this function. When k takes any of these values, it goes into that function. So if I put 12 in, what's the probability that we get at 12 when we roll two dice? Well, we get 13 minus 12 over 36, which is going to be 1 over 36. And that matches nicely up with what we had earlier. And suppose, what was the probability that we get a 2 when we roll two dice together? Well, I will sub the 2 in here. So we get 2 minus 1 over 36, which is as well is 1 over 36. So we can see our function works nicely here. Okay, so suppose I wanted the probability that x equals 3. So I'm going to use the the function as opposed to the probability distribution table just to answer this question. So the probability that x equals 3, well, that means I'm taking the value from here, so it's going to go into this function. So substituting k equal to 3 in, 3 minus 1 is 2 over 36. 3 minus 1, so we get 3 minus 1 over 36 equals 2 over 36. And as well, that matches up nicely with what we should know the answer should be. What about the probability that x is greater than 9? So that means I need the probability that that x is 9 plus the probability that x is 10 plus the probability that x is 11 plus the probability that x is 12. So I'm going to add these all up. So we're going to do 13 take away 9 over 36. 13 take away 9 over 36 plus 13 take away 10 over 36 plus 13 take away 11 over 36 plus 13 take away 12 over 36. 13 take away 9 is 4 over 36 plus 3 over 36 plus 2 over 36 plus 1 over 36. And adding those all together, 4 plus 3 plus 2 plus 1 is 10 over 36. And if we went back to our probability distribution table, does that tally up with what we've got? What is the probability that x is? Oh, I've made a big mistake here. I have included 9 when I shouldn't have, because it's x is greater than 9. So I'm glad I referred back to my table. So let's take that out. So my answer is not 10 over 36. It is in fact 6 over 36. 6 over 36. So, does that match up with what we've done so far? And with our table, it should do. 3 over 36 plus 2 over 36 plus 1 over 36 is 6 over 36. And again, let's refer back to the two-way table. What is the probability that when I roll two dice, I get a value that's greater than 9? What's the probability we get a value greater than 9? Well, it's these outcomes down here. And there is 6 out of 36. So that worked out nicely. Okay, let's have a look at another example here. So I got a probability function. I need to work out k and hence draw the probability distribution. So when x is 1, 2, 3, 4, I'm going to use this part. When x is 5, I use this part. So let's let x equal 1. So when x is 1, we get 0.3 times 0.7 to the power 1. And 0.3 by 0.7 is 0.21. Okay, when x equals 2, I got to do 0.3 times 0.7 squared. And let's take the calculator out for this. 0.3 times 0.7 squared, 0.147. Okay, when x equals 3, we get 0.3 times by 0.7 cubed. So I'll just delete that and change it to cubed. And we get 0.1029. 1029. When x equals 4, we get 0.3 times 0.7 to the power 4. Plug this into the calculator. Let's put it back in regular mode. 0.3 times 0.7 to the power 4. 0.07203. 0.07203. Okay, and when x equals 5, we get k. So when x is 5, the answer is k. Now I need to work out k, and remembering that the sum of the probabilities must add to 1. When I add all of this up, so 0.21 plus 0.147 plus 0.1029 plus 0.07203 plus k must equal 1. So I'm going to take everything, take all of this jazz away from 1, and then that will give me k. So 1 minus 0.21, 0.147, 0.1029, 0.07203. So we get 0.46807. So k equals 0.46807. 46807. Okay, excellent. Now we know what k is. We should be able to draw our probability distribution. So, to draw the table, we're going to have the particular values of x, which could be 1, 2. I think I'm going to need a bit more space, so let me make a bit more space to fit all these decimals in. So we got 1, 2, 3, 4, and 5. And the probability that x equals x, which, by the way, can sometimes be just written as a small p for probability, is, let me see, the first one, when x is 1, when x was 1, we got 0.21. So when x was 1, we got 0.21. When x was 2, we get 0.147. When x was 3, 0.1029. When x was 4, 0.07203. And when x was 5, we got k, but we know that k is 0.46807. And if you want to check your answer, add up all your probabilities. They should add up to 1. Alright, time for you to have a go now. So pause the video and work out k and then draw the probability distribution. Okay, hopefully you've managed to go with that. Here are the solutions. So we took a similar approach. We substitute each value of x in, which gave me 0, 4k, 2k and 8k. I know that when I add up all of these, they have to add up to 1. So I found out that k was 1 over 14. Once I know that k is 1 over 14, I can fill in my distribution table. Because when x is 1, we get 1 minus 1, which is 0. 0 times 1 over 14 is 0. When x is 2, it's going to be 2 times 1 over 14 times 2. So 2 times 1 over 14 times 2 will give me 4 over 14. When x is 3, we get 2 times 1 over 14, which is 2 over 14. And when x is 4, we get 2 times 1 over 14 times 4. 4 gives me 8 over 14. And when I add up all my probabilities, we find that it adds to 1. Okay, one more example. And it's going to come from cumulative distributions. So if you remember, we've been using cumulative frequency an awful lot. Cumulative distributions, you just think of cumulative probability, and it uses this notation here, which is a large f of x. Okay, not the small f of x you'll be used to from doing functions in your core. It uses the large f, so a big F of x. And big F of x simply means the probability that x is less than or equal to a particular outcome. And that's what we call the cumulative distribution for a random variable x. So just to kind of really solidify our understanding here, the first value will always be the exact same as what we're used to from our probability distribution. The second value is simply the first value plus the second. So 0.5 plus 0.3, which is 0.8. And the last value is this value. So we're taking a cumulative probability. 0.8 plus 0.2 is 1. You'll notice the last value is always equal to 1. Always equal to 1. And the first value will always be the same as whatever the probability distribution had. Right, so let's take a look at an example now. So suppose a random variable x has a cumulative distribution function given here, and I'm asked to find k. Now one thing I know is that the last value, alright, these are the particular values x can take, 1, 2 or 3. The last value, or f of 3, must equal 1. So that's important. So let's use that fact to answer this question. I know when x is 3, I know that must equal 1. So cross multiplying now, I'm going to multiply both sides by 25. So that means that 3 plus k squared equals 25. And now I'm going to take the square root of both sides. So 3 plus k equals 5. And then finally, taking 3 off both sides, k must equal 2. So I know that k equals 2. Now I can draw the probability distribution. So that's what we're going to do. We're going to draw the probability distribution for x, the probability that x equals x. The particular values we have for x are 1, 2, and 3. So 1, 2, and 3. Right, so when x equals 1, when x equals 1, in fact, let's not do the probability distribution table. Let's do the cumulative distribution table first. Let's start with the cumulative distribution table. So we start with x and f of x. 1, 2, and 3. I know the last value must equal 1. The first value, well, we know that k equals 2, so let's work out f of 1. F of 1 will equal, well, x is 1, so you get 1 plus k is 2 squared over 25. 1 plus 2 is 3. 3 squared is 9. So we get 9 over 25. So I know the first value is 9 over 25. We can work out f of 2. So putting 2 in, we get 2 plus 2. Let's do this in green. F of 2 equals 2 plus 2, which is 4. 2 plus 2 to be squared all over 25. So that's 4 squared over 25, which is 16 over 25. So I know that this part is 16 over 25. Now that's going to help me do the probability distribution, probability that x equals x. Well, the first value must be the same. It must be 9 over 25. If the next value is 16 over 25, but the previous value was 9 over 25, that means I must have added 7 over 25. So 9 over 25 plus 7 over 25 gives me 16 over 25. And then finally, I know it's 16 over 25 here, and the last value is 1. That means I must have added 9 over 25. Yeah, 9 over 25, 16 over 25 plus 9 over 25 is 1. And just double check our answers by making sure that this adds up to 1 as well. 9 and 7 is 16, 16 and 9 is 25, so I know that both of these solutions are correct. Right, last part, I want to find f of 2.7. Well, because it's discrete data, that means I'm essentially looking for f of 2. F of 2. Because I cannot have anything in between. The only values I have for x are 1, 2, or 3. So if I want f of 2.7, that means that's the same as saying f of f of sorry, not f, p of, it's the same as the probability that x equals 1 plus the probability that x equals 2, and if you like, the probability that x equals 2.7. But there is no value for that. That part here is 0. There is no value for that because the values you can take are only 1, 2, or 3. So this one is 0. And f of 2, there's two ways we can get it. We can clearly see it's 16 over 25, but if I want to use it this way, it's going to be 9 over 25 plus 7 over 25, which is 16 over 25. Okay, that's the example done, and the last example of this video. Time for you to have a go now, so pause the video, find k, draw the distribution table for f of x, draw the probability distribution table, and then find f of 2.7. Okay, hopefully you've had a go at that. Here is the solution now. So we got our distribution table and our probability distribution table. The value of k is 5, and the last part is 7 over 8. Right, hopefully you found the video useful. I'll be back again soon with another video. Best of luck with revision, and I'll talk to you again sometime. Take it easy. Make sure that you try also exercise 8A and 8B. Bye for now.